Welcome everybody. So today's webinar is going to be about Langmuir probes. The title is Probing Plasmas, Applications of Langmuir Probes in Plasma Diagnostics. Big thanks to my colleague, Dr. Anshu Verma, who helped put together this presentation. And before we get started, there is a little Q&A box. Type in questions as we go along, and at the very end, I'll answer any questions in the Q&A. Okay? What else? And this the recording of this will be available afterwards. So if you miss it or you want to share it with someone else, it'll be available on impedance.com/videos. Right, so let's begin. I'll start by giving you a little outline of today. So we have done a Langmuir probe webinar before, which was fully on theory. It was very mathsy. I'm going to simplify it back a little bit today and more focus on applications. So we're going to start back at the basics. What is a plasma? What are the fundamental parameters? And I want to, like with other webinars, kind of give you an intuition, a feeling for how things are changing as you change the power, the pressure, the gas. So how are these fundamental plasma parameters changing? And we'll spend about 10 minutes on that. Then going to introduce Langmuir probes, like what are they? How do they work? I'll talk a bit about the construction, maybe mention some of the basic theory, like what kind of parameters you get from it. And then we're going to do a live demo. So downstairs, we have several plasma chambers here in impedance. And we have a Langmuir probe in one of our capacitively coupled chambers. So it's a 300 millimeter chamber, a CCP. We're going to run argon at 2 Pascal, 13.56 megahertz. We're actually using two sources on the chamber. And for about 15 minutes, we're just going to play with the probe. So we're going to run CW plasmas. We're going to change the power and see how things change. We're also going to do pulse plasmas and look at time resolved measurements. And in general, I'll give you a tour of the software and what we can do with the probe and this sort of thing. Okay. After that, we'll flick through a few case studies. So just to give other examples of what people are using it for, like uniformity profiles, just a characterization, what people are learning from pulse plasma characterization. But I'll go through these fairly quickly. And then at the very end, we'll have a Q&A. So again, as we're going through the presentation, please fill in the Q&A section. I'll answer everything at the end. And if there's time as well, I do have a backup, which is loads of maths. So if people are interested in seeing Langmuir theory or going through it a little bit, we've taken all the slides from the previous webinar into this one. So, but we don't have to go through that. That's optional, depends on how we do for time. Okay. So let's begin. Very briefly, just for those of you who don't know us, I work for Impedance Limited, which was founded in 2004 by Professor Mike Hopkins. We're based in Dublin, Ireland, quite close to the airport. Like you see the planes flying over all the time. And we're about 40 employees, not including global distributors. And our whole point is we want to be able to provide plasma and RF measurements to the industry. So we try to make the very best probes, and we're always improving them, adding new features, exploring new applications. So if you're working on something that we haven't touched on today or in previous webinars or whatever, reach out to us. Chances are we've actually done something. We work with everybody around the world. We mostly work with semiconductor, but also universities and research institutes we work quite closely with. We have many research partners. This is the sort of portfolio that we have. The last couple of webinars have focused on plasma surface interactions with our Semion devices and RF measurements and how they link to plasma surface interactions. So the previous tailored waveform webinar looked at these things as well, like these two simultaneously. Today, we're going to be getting some data from the Langmuir probe. So let's go. Look, let's start at the basics. Before we go into depth, we have to make sure everyone's on the same page. So, we're going all the way back to early science classes, what is a plasma, right? So those of you who use plasmas but don't know why you're using them, I was in a plasma lab last week and plasma was very much actually a tool to be used to achieve something without understanding how it was being achieved. So let's start at the beginning, right? So simply put, plasma is an ionized gas with collective behavior. So that's kind of what makes it a plasma. It's not just random ions, it actually has collective behavior. And usually, even if you look at a plasma, like we'll show some pictures soon, it's like this big glowing gas, right? Typically 1% or only less than 1% of it is actually ionized. It's still mostly neutral gas in there. You can bump that up to 10% in some really high density systems, but in general, they're mostly neutral gas, okay? And one thing to note, this is kind of a finicky point, but plasmas cannot be stored. So what I mean that is you have to apply constant power to sustain them. So whenever you look at plasma papers, we're talking about we're using this power, this pressure, this gas flow, whatever. You do need to provide power. As soon as the power goes off, everything will return to neutrals and the plasma disappears. Some of the products of the plasma remain. So, for example, plasmas produce a lot of radicals, and radicals can stick around for a long time. Like radicals can have lifetimes where you can put them in a bottle and carry them to another lab, right? So some radicals have very long lifetimes. But today is more on the electrons and ions. And understanding plasmas is difficult. Whenever someone calls themselves a plasma expert, you can definitely catch them out, right? Because to fully understand plasma, it's like chemistry, kinematics, electrodynamics, thermodynamics. There's even quantum physics stuff going on. So, for most people, plasmas are black boxes. So I'm going to start this presentation by trying to give you some intuitive feel for what's going on inside a plasma. And just as a general rule, the idea you have solid, you add some heat and it becomes liquid, you add more heat and the particles can break free of their kind of intermolecular bonds and you get gas. And then if you keep on adding energy, eventually electrons start splitting off from the atoms of molecules and you end up with positively and negatively charged particles in the plasma. You can have not just electrons, but negative ions too, depending on the gases present. Okay, so regarding understanding plasmas, there's a huge amount of diagnostics out there. There's many ways to look at them. Many labs would have things like mass spectrometers, which residual gas analyzers. They would have OES, optical emission spectroscopy. They're very common. But the Langmuir probes, which is the focus of today, are a type of electrostatic probe. So it's about measuring the electrical properties of the plasma, which is usually what you care about. Like what makes plasma special is that because they're electrified, you can control them with voltages. You can do very fine engineering with these. So with plasmas, what do we need to know? Because there's so many properties, right? But in general, all you need to know for most applications are these two following things, okay? You need to know what the ion density is, okay? It's also called the plasma density. So plasma density could mean ion density or electron density, okay? So for ion density, it's how many ions per unit area. For electron density, how many electrons per unit area, okay? And these densities can span a really wide range of values, depending on what pressure you're using, how much power you're applying, and what technique you're using to apply power. So in kind of research chambers like what we have downstairs, it's like 10 to the 14 to 10 to the 15 per cubic meter densities. In semiconductor processing, it's usually 10 to the 16 to 10 to the 17, so a bit more dense. If you're using an ICP chamber, you can even, like in the ICP section, get up to 10 to the 18 per cubic meter. And then if you're using a microwave electrocyclotron resonance, ECR plasmas, you get up to 10 to the 19 and beyond. So there's different powering mechanisms for plasma using different frequencies, and that's kind of a topic for another day. In general, this is kind of the range of densities that you get in different plasmas. And there's a few reasons why you care about density. One of the main ones is this is related to how fast the product will be processed. If you have more ions hitting the surface, your etching will happen faster. It's as simple as that. So you need to know this number to work out how long do I have to run this to get this thickness, this amount etched, okay? The other thing is the electron temperature, which is how hot the electrons are, okay? And this is what controls the plasma chemistry, okay? Electrons are extremely hot in plasmas. So typically they're 1 eV to 5 eV in industrial chambers. Like that's a typical range, maybe a bit higher end sometimes, but you don't get numbers much higher than this. And just for context, a 1 EV electron is the equivalent of about 11,000 degrees Celsius. So, if you just were purely applying heat, like not, RF voltages, currents, whatever, if you're purely applying heat to get this temperature electron, you'd actually need 11,000 Celsius, which is huge. And this is what makes plasmas really special, what gives them so many applications. You can do 11,000 degrees Celsius chemistry at room temperature, okay? Because electrons have so little mass, they're not like going to heat anything, okay? Really, they're not, you can process fabrics, you can process food, and you can get the sort of reaction rates in chemistry that you'd otherwise need 11,000 degrees or 100,000 degrees to get to, but you can touch it, right? So this is what makes them so special. And one other thing to note, in RF-driven plasmas, it's called a non-equilibrium plasma. So what that means is the ions and electrons are not at the same temperature, So usually if ions are 40 degrees Celsius, or the electrons, I suppose, if you have 40 degrees Celsius, but it's not like that. The ions, like if you're applying high frequencies, the ions can't really react very much. Like, they don't absorb so much energy from the voltage going up and down. Okay, they have too much mass, too much momentum or inertia or whatever to move. So the ions actually stay pretty close to the gas temperature, but the electrons, they can see that RF voltage. They see the bit, 1,000 volts or whatever, and they will move with that. So the electrons pick up all the energy. Okay. So this means that the ions are at low temperature and the electrons are high temperature. So that's what makes it special. So let's get into some intuitive understanding of what's going on with plasma density and electron temperature in different scenarios. Okay. So how does a plasma change with power? So here's some nice pictures where you see a low amount of power and it's very dark in there, and you have a little bit of plasma around the top electrode. Raise the power up and you get more plasma forming, and raise it, and you can see the plasma expanding out. So as you expect, more power means more density. Okay. One thing to keep in mind is that a lot of people develop processes or they're trying to match processes by making sure the RF generator power is the same. You have to remember that the matchbox is not 100% efficient, so you actually have variable power reaching the electrode as the matchbox heats up, or as the transmission line heats up, it gets more resistive, you have more power losses. So 700 watts of your generator might be 650 watts at your electrode, and then as everything heats up, that's slowly dropping down. So just keep in mind that the density, because of the power delivered, changing versus during process, the density is not constant. It is drifting during the process. Okay. Regarding kind of modeling what the density is, so it's related to the power. The density is also related to the chamber geometry. Okay. So this A effective is basically what's the surface area that the plasma is exposed to. Okay. And then these other numbers here are just related to how quickly charges are being lost to the walls. Okay. This is why I try to bring home the point that if you spend months and months, sometimes only weeks, but if you're spending months developing a perfect process that you get the exact features you want on the exact scale you want, and no surface roughness and all this sort of stuff, and you develop that in a chamber with power, pressure, gas flow, it is meaningless. If you move to a different chamber with a different geometry, you're going to have to start from scratch because you have a new plasma with all the change in geometry. Like even if you have a bare aluminium chamber or bare steel versus like an anodized aluminium or an insulated material, you have different plasmas, right? Different densities. So matching the power density, matching the plasma density is what you really want to do chamber to chamber. You should know this if you want to like match the whole chemistry going on. Now the walls also play a part in chemistry, but that's another story. What about versus pressure? Okay. And this is something that is important to consider. Okay. So the impact on pressure is less intuitive. There is actually kind of a maximum plasma density you can reach. There's like a peak density at a certain pressure, and above and below that pressure, you drop density. So it's kind of like a parabolic shape. Okay. And the reason for that is, below a certain pressure, you just have less neutrals available to ionize, right? So the density is just going to go down because there's not so much to ionize. And then above a certain pressure, you have more collisions with neutrals, and those are absorbing more energy. So there's less to ionize available. You have like vibrational states and rotational states and other mechanisms of just pure heat, which is reducing the ionization that can happen. Okay. So anyway, here you can see a case where at one pressure, you have plasma all across the chamber. And as you increase the pressure, the plasma becomes a bit more confined towards the electrode and confined at the bottom. And then eventually you're at the point where the plasma is fully confined to the electrodes. There is a kind of name for this. We call this a transition from collisional to collisionless in plasmas. So the idea is, if you think of electrons moving in a plasma, collisional means that it travels from one electrode to the other on average without a collision, or there's very few. And collisionless is that, and then collisional is where very few electrons will make it from the top to the bottom without a collision. So it's about looking at the mean free path based on the pressure and the gas and the electrode distance. You have to be very careful not to develop a process where you're on this transition region, because you can have a very sharp change in plasma properties over a small pressure range. The kind of pressure range that could come about because your electrode or your pressure gauge is recalibrated or something. Okay. Also, the pressure gauge accuracy matters. So some pressure gauges have like a 15% accuracy at one pressure and 3% accuracy at another. Make sure you know your pressure gauge. As kind of a sanity check, if your pressure gauge is right, check pump down times. Okay, especially after a pressure gauge calibration. So if you're reaching a target pressure, that should take a fixed amount of time. Okay, with the pump speed you have available, we assume that's going to be constant. If your pressure gauge calibration changes things, your pump down time will change, because in reality, maybe you have to pump more to reach the pressure, your target pressure. So that's a sanity check. And then what about gas? So you've all seen this before. As you have different gases, you get different colors. Okay. So, but different gases is not just about changing color, it's about changing the chemistry. But that's then also changing the plasma density and electron temperature. Okay. So for example, there's also electropositive versus electronegative gases. Some gases like SF6 or anything with fluorine in it basically attracts electrons. So you get a lot of electron absorption to make negative ions. And that's going to, with fewer electrons present in the plasma, you lower the overall density. So usually, say oxygen can form negative ions. For the same power and pressure, an oxygen plasma is usually a lot dimmer than an argon plasma. And that's because the oxygen you're not getting as much ionization, you're absorbing electrons. You do get a lower density plasma in the same situation. So again, matching power and pressure doesn't matter. So if you have, for example, a small air leak, suddenly you have nitrogen absorbing a lot of energy with its rotational vibrational states, and you have oxygen forming negative ions, which is going to bring down the ionization rate. So like air leaks really change the plasma a huge amount, even a small percentage. Yeah, so I hope this gives you a kind of feeling for what to care about. Changing pressure and changing the gas and changing the pressure also changes where you are on the Paschen curve. So there's some instances where your pressure and power might make it really, really hard to strike your plasma. Okay, so keep that in mind. Sometimes like raising the pressure a little bit or adding a couple % of argon for just a second can help you strike a otherwise hard to strike plasma. And then you can turn off the argon and deal with your normal plasma. Right, so finally we're reaching Langmuir probes, a little bit behind schedule. Downstairs, actually, this is the exact chamber we're going to be taking measurements in. So downstairs, this is what's set up. We have a Langmuir probe immersed into a CCP, 300 millimeter electrodes. We're actually powering the top and bottom electrode, like this is grounded here, but we're going to be powering both. Yep, we just have a Langmuir probe stuck in there. So what is a Langmuir probe? And in essence, it's a wire in the plasma. Okay, it's a little bit of metal, conducting metal in the plasma. And like you can see this schematic here. So you have a metal wire, you have some sort of insulator, and then you have something that maybe protects it from the plasma or the local environment, like the whole tube. This wire, the idea is you immerse it in the plasma and you sweep a potential across it. When your potential is negative, you're going to attract ions and repel electrons. When the potential is positive, you're going to attract electrons and repel ions. And then the transition region is going to tell you a little bit about, the distribution of electron temperatures and stuff like that. So it's really, in principle, quite simple. Now, the analysis of the data is another thing, but these probes are they can be made compatible with practically any plasma. I'm actually going to show you a list of what it's compatible with a little later. And with these Langmuir probes, there's different geometries. So I mentioned that, typically you use what's called a cylindrical tip, which is really just like literally a piece of thin wire. Okay. But, you have to take into account different mathematics depending on the geometry here. So there's also commonly like big spherical tips, and there's what you call planar tips, which are small flat ones. And these, they have the same behavior when you're in this region. So I mentioned earlier, when you have a negative voltage applied, you block block electrons, and you only bring in ions. So you get a small ion current here, which is used to determine the ion density. In the next slide, I'll actually go into more detail on this curve. And then there's a transition region, and then there's what's called the electron saturation region. So when you're drawing in lots and lots of electrons only, and the more voltage you apply, the more electrons you draw, pretty much. Depending on the geometry, the behavior here is different. So we have had clients before saying to us, come to us and say, hey, we expect this, why do we see this? And it's like, depends on the geometry of your tip, you know. So what happens is at some point, as you increase the voltage that you're applying, you actually start changing the size of the sheath that forms around the surface of the probe. And as that gets bigger, it's effectively like a bigger collection area. So you collect more and more and more. And how that grows will depend on obviously the shape of the probe. Okay. So, you know, planar probe, you don't get sheath expansion. Like the collection area and the geometrical area stay pretty much the same. And then with spherical, you get this very rapid expansion because you have like a full sphere expanding out. And with the cylindrical, it's kind of somewhere in between. So just showing, this is a screenshot from the software, but it sort of gives an idea of what plasma parameters you can extract from a Langmuir probe curve. So I mentioned earlier, we care about the ion density and electron density. So ion density comes from this electron saturation region. The electron density comes from this, the electron saturation region, which is here. This region here is also the plasma potential. So this is at this point, the probe is kind of like a multimeter. Like if you stuck one side of the probe in the plasma and the other side against the ground, the plasma is usually positive with respect to ground because you have electrons being lost to the wall faster than ions, and you have the sheath formation, blah, blah, blah. But this is where the plasma potential is, so we can measure that. And this is important for knowing at what energy are ions hitting a grounded surface. Now, if you have a biased surface, you have to add the bias to the plasma potential. There's also the floating potential. So this is if you have a insulating substrate or a non-grounded electrode. Let's say there's an RF driven electrode, but the RF is off. It'll go to the floating potential. This is where electrons and ions balance out. And that's usually some small positive voltage, like in this case, like 3.6 volts, where the plasma potential was like 14. So this gives you an idea of what floating surfaces go to, and then the difference between the plasma potential and the floating potential is what energies you get. So you get lower energies with insulating materials typically. You get other things. You get the electron temperature, which comes from this transition region here. The analysis is a bit complicated. It's covered in our other Langmuir webinar. But this number is like 2 point something. I mentioned earlier, it's usually between 2 and 5. Can be a bit higher than that. And that's it. You also get some calculated parameters like the Debye length. So this gives you information about sheath thicknesses and over what range the plasma is doing electrical shielding and so on. A little bit on construction before the demo. So if you wanted to build your own probe, essentially you need to have a high temperature material for the probe tip, because when that's drawing electron currents, that can get really hot. Later on, we might actually show you they're happening in our chamber. So you usually use like tungsten or tantalum, have really high temperatures. You also have to choose the tip based on chemistry. So if you're in like an oxygen plasma or something that will react with and burn tungsten, you use something like platinum. Tantalum is a good all-around material, like has low reactivity and high temperature. Like it's a good, but platinum is like the best for like oxygen plasmas or something. You need to make it so that the tip has a known size. So you have to have like an insulating material. And of course, inserting a probe does disturb the plasma. So the idea is you make the tip very, very, very thin, so it's not disturbing the plasma, like 100 microns thick or 200 microns thick. And then you slowly taper up to the shaft. So this is why here it's thin and it's a little bit thicker, then a little bit thicker. So the part that's really disturbing the plasma is far enough away that it makes no difference to the measurements. And then inside you have some cables so that you can apply the voltages and measure the current, and you need some connector on the end. And then, of course, at some point, you have to have a vacuum interface, okay? So it's relatively simple to build your own basic Langmuir probe. And it's kind of a rite of passage for many plasma physicists to build their own Langmuir probe. So I built my own, and many of my colleagues have built their own at some point. The other thing you need to build is the electronics. And the electronics is pretty simple. You just need to be able to apply a sweeping voltage and measure the current. So the circuitry from that is fairly straightforward. And in terms of installing in the chamber, this is kind of how we have it downstairs, just probe against a vacuum flange. This goes in, and then the measurement tip is somewhere in the middle. That's going to the electronics box, and then that's going to a computer. One other thing to consider if you build your own Langmuir probe is you have to, if you're using an RF-driven plasma, you have to compensate for that. So basically, we mentioned earlier plasma potential is some number. In reality, the plasma potential is going up and down with the RF. Which means that the plasma density is also moving with the RF. Now, the average is typically all that matters. So what you want is that the Langmuir probe tip will float up and down with the plasma, smoothly. So that means it's always kind of seeing the same plasma voltage, relatively speaking. That's done by putting these high impedance filters in line, like usually inductors. And you want to kind of have a minimum of 100 kilo ohms impedance on those inductors at the frequency you're operating. So if you're operating at 13.56 megahertz, you want a filter that has, when you do like a VNA sweep, like here, that at that center frequency, you have at least 100 kilo ohms of impedance. The higher, the better. So sometimes you might put more than one in line, and they sum up in series. Also, plasmas produce harmonics. So make sure if you put in 13 meg filters, you also have 27 meg filters in there somewhere for the second harmonic. And this enables you to get the cleanest possible data. So the probe we're using today has these built-in RF filters right up at the tips where they're meant to be, so the tip will flow perfectly with the RF. Lastly, if you build a Langmuir probe, where can you use one? And they're obviously applicable in low temperature plasmas like CCPs, ICPs, ECRs. This is like what we're going to be testing in downstairs. They can be used in deposition plasmas like magnetron sputtering tools, high PIMS tools, PECVD tools. And, Langmuir probes have self-cleaning capabilities, or you can repel ions, or you can keep a voltage on the tip so you're constantly sputtering particles. So they are usable in deposition plasmas. As a rule of thumb, as long as your deposition rate is less than 200 nanometers a minute, you can deal with it with a Langmuir probe. Above that, you have to use a special type of Langmuir probe, which we do have available. Etching is fine. You just occasionally might have to replace the tips if you're etching them away. So, but usually you're not really. You're just dealing with plasma potential energy. So they're perfectly fine in reactive ion etchers or any sort of etching tool. They can be used in thrusters and ion beams as well. An ion beam is a thruster is an ion beam. And they can also be used in things like laser-produced plasmas, even high-pressure plasmas. So we've been making really good progress with getting plasma measurements in atmospheric pressure plasmas, like atmospheric jets. We're getting good data from those now. So we have a PhD student working hard on that up in Queen's University. And we're looking forward to presenting some results on that in a future webinar and some conferences upcoming. But I think we kind of cracked these sort of measurements. Where it's not applicable is usually like fusion plasmas. Probe gets way too hot. You have to build special actuators to bring the probe in and out of the plasma. Really high temperatures, like we build probes up to 900 C, but there's even higher available than that. So you just have to choose the materials. Not impossible, just difficult. And where there's really high local voltages. So if you're trying to do this little plasma sweep of plus or minus 50 volts or something, but you have 10 kilovolt right beside the probe, the plasma is going to collapse and the 10 kilovolt is going to go to that little sharp lightning rod tip. So the plasma collapses and you can't measure it. So these are tricky, and you have to kind of look at other methods there. We after the demo we can go into the applications, but people do uniformity measurements within your drives, angular measurements like say in thruster plumes, temporal measurements. So if you're doing pulse plasmas, these things can have really high time resolution. You can do kind of in situ measurements for process repeatability. Is my plasma the same as it was yesterday, or is it the same tool A, tool B? And lastly, this is a whole topic on its own. You use the data you get from a Langmuir probe in order to model the chemistry that's happening in the plasma. So I mentioned the electron temperature, specifically the electron energy distribution function, because you have electrons at different temperatures available, like different energies available. Those drive the chemistry of the plasma. Okay, so if you know this data, and you know the plasma density, you can specifically the electron density actually, and then the neutral gas density. You can start doing these models where you use collision cross sections in order to get exactly how much of each species you have in the plasma. So if you have a molecular plasma, it's very complicated. You can then use this to model, okay, what's my amount of, let's say hydrogen plasma, how much H plus do I have, H2 plus do I have, H3 plus do I have? If you have a water vapor plasma, then okay, how much also oxygen do I have, and negative ions, positive ions. So these are the raw numbers you plug into those models to predict all that. And something I've done before. It's not even too hard to do this like series of differential equations and you solve them together. It's not so hard. Like MATLAB can do it, and some Python programs can do it easily. So, but these are the fundamentals for them. With all that said, let's get into the live demo. So I'm going to stop sharing the screen, and we're going to swap to my colleagues downstairs. So Sarah, I'm going to make you the host, and then if you want, you can share your screen. You should be host now. You should be able to share the screen. Okay. Perfect. Okay, so what we're looking at here is the Langmuir probe software. So before we run a scan, I'll just give you a quick tour. So Sarah, can you click on the settings button there? Yeah, so when you're setting up a probe, in order to do all the modeling, like we skipped the maths today, but the modeling requires, we need to know how much our collection area is on the probe tip. We need to know the dimensions, like the probe radius as well as the length. We need to know the ion mass. We need to know if there's any resistance across the probe from the inductors, so that you can compensate for voltage drops due to that current on that resistance. We need to know the local gas temperature, and we need to know the pressure. And with all these combined, we can do all the state-of-the-art models and sheet corrections and orbital motion, limited theory corrections, and et cetera, right? So this handles all that. So that's okay. Sarah, you can get out of there. And maybe let's go through the config real quick. Excuse me. So on the config there, we set the integration time. So the integration time is, we have a probe that's sampling at 80 megahertz. And at, we can do constant averaging during that. So this is saying do 1,000th microsecond averaging during the 80 megahertz sampling. Down below, we have some data acquisition numbers. So how many times do we take a measurement at a certain voltage and average them together? And like say the bottom one there, traces per scan. This is like take many scans at the same time, pretty much, and use that to determine what the error bars are, basically, like what does the measurement error bars are. So like if you take 5 measurements, we look at what the max and the min numbers are from the theory, and then we can use that to put an error bar on the data, which you'll see in the table in the top right there. Can you also show us maybe the multi-scan page there? So we do have the option to do like spatial scans. Now today we don't have a linear drive available, but usually you just set the start position, end position, and the drive will move across the chamber and get uniformity profiles. There's time trend, which we'll use to show like variations in the plasma versus time. Can you go to voltages there, Sarah? So you set a voltage range, usually -20 to 50 is fine for a single probe, and then you optimize that depending on your plasma chamber. Maybe let's look at cleaning. So the probe has cleaning capabilities, which is necessary in, both in etch and in depth, because in etch you're sputtering material. So you may need to be, or some etch processes, produce polymer layers. So you want to regularly clean the probe, so you can automatically clean it. And the way it's done is you apply a large positive voltage while the plasma's on. It draws a lot of electrons, and that superheats the tip. So if we have time later on, we'll show you that the superheated tip, glows white hot and removes all the material and makes it clean again. And then maybe advanced. We don't need to look at pre-scan. Yeah, advanced. So the other thing is, depending on the plasma you're measuring, you might have low density, high density. So there's different current ranges available on the box. Okay, so this is applicable over then a wide range of those, 10 to the 14 to 10 to the 19 or whatever. This will come from choosing these channels, the available channels. I think we can leave that there. So so I assume at this point the plasma's on. Will we try a scan at 100 watts? So it's argon, CCP, 300 millimeter electrode. Make sure you turn on the box, please, if you had it turned off. Yeah, you can reset the box, don't worry. So we're in a CCP chamber. The electrode gap is fairly big. It's like 50 millimeters or something like that. Yeah, we're running argon, about 2 Pascal pressure. and we're running 13.56 megahertz to the bottom electrode through a matching box. So whenever you're ready. The other thing, Sarah, you may have to start a new session because of whatever happened. Oh, you run it clean, so it's doing the relaxation time. Sorry. So you see in the bottom corner, if you run it clean, the probe does it as a cooling moment. There we go. Perfect. So we'll take you through the table up top there. So this is a sweep that just happened. And in the top you have VP. So that's the plasma potential. So in our chamber it's like 31 volts, fairly high. We have the floating potential of 22. So that's basically related to the electron temperature. The electron temperature is about 2.52 eV. And then our plasma density is about 3 by 10 to the 15. And actually, if we look at our ion density there, 3 by 10 to the 15, and electron density is 3 by 10 to the 15, ion density is 4. So they're quite close, and that's what we want. There's more likely to be an error in the ion density than the electron density because of we get much lower currents in the ion region, which is to the left of the graph. There's actually more than one way of getting electron density because we also measure the electron energy distribution function. So there's another electron density just below, and that's 3 by 10 to the 15. Yeah. So the top value is assuming a Maxwellian distribution in the plasma, and the bottom value is a temperature gathered from the electron energy distribution function. And it must be Maxwellian then if they're nearly the same. So Sarah, can you click on the view EEPF just under view scan and then right click twice so we can see it? So this here then from the transition region is the electron energy distribution function or probability function. We won't go into all the details here, but effectively, this is how many electrons are at each energy. So on the bottom axis, you can see going from, about 0 eV, I guess, all the way up to about 30 eV. And this is a log plot. So that's why we have a straight line, and that's telling us that it's Maxwellian. Okay. You can also see error bars on the data. So that's because we did 5 traces in the background, and those 5 traces, we took the max and the min to work out what's the range of parameters we get. And that range gives the error bars on the graph, and also the percentage errors up in the top right table there. And you can see the errors are actually quite low, like 1% or less than 1%. So the variability is good. What we'll show next. So Sarah, can you click back on view scan? And then let's change the powers. So can you go to config and the multi-scan? And we'll do a time trend, maybe make only 10 seconds long. Yeah, you can see at the bottom, by the way, if you don't mind showing in, the sensor estimates how long a scan is going to take based on our settings. So we see our estimated scan time is about 8.55 milliseconds. So we have various timing, we have settling delays, we have averaging added, we have multiple traces happening. Even with all that, it's taking less than a second. We can get those numbers all the way down to like you can get scans on like 30 microsecond or something kind of scale. Anyway, you can get those numbers way down. Actually, the best we can do on this is 12.5 nanoseconds, but we'll do that a bit later. So we've set 10 scans to happen 1 second apart, and a scan is taken less than a second, so this should be fine. And then what we're going to do is we're going to sweep the power from maybe 50 watts up to 200 watts. So we'll just do a smooth sweep of power, and then we'll look at how the electron density, ion density, plasma potential all changes versus power. So whenever you're ready, run the scan and please sweep up the power. You can see in the bottom corner, you'll see like a bar going up. So 83, 85, 90 something, and now 100% complete. And you'll see now, yeah. So we have a scroll bar, and with that scroll bar, we can have a look at the raw IV curves at each point, okay, during the scan. But if we go to the bottom and click View Trends, there we go. So that's plasma potential versus power. Can one of you tell me what power you set to? Was it like 50 to 200 or something?
Yeah, 50 to 200.
Thanks, Jordan. So you can see how the plasma potential went versus power. Can you click on electron temperature? Okay, so electron temperature was fairly flat. So it only went from 2.4, 2.5 down to 2.3. So the electron temperature is like very dependent on geometry. We don't expect it to change that much. It's going to be the same region versus power. Can you click the electron density maybe? There we go. You can also see then the electron density increase with power. And what you'll see is, the electron density is not linear with power. In fact, if you keep plotting this way out, it's approximately square root with power. So, doubling the power is not doubling your ion flux. It has this sort of dependence. And actually, this dependence even depends on the frequency you're using, because your chamber, even though it's a capacitively coupled plasma, there's inductive coupling happening there. And the proportion of that depends on the frequency and depends what power you're at. So it's not so straightforward. So yeah. Right. Can we do so we did a power sweep, we did a fixed position sweep. Can we do maybe we try pulsing the plasma? We try pulse, Sarah? Setting a pulse off will take a moment. We have to swap the cables around, and we're going to put the pulse generator on against the matchbox instead of our CW, so it may take a minute or two. If you go, Sarah, to the so we'll just explain this here. So we've switched from time average mode on the top to time resolve mode in the middle there. On time resolve mode, you can set your step size, your start time, and end time. But the start time we're setting is 0, and the end time we're setting is the whole period. And the step size, we're going to do 30 microseconds. Now you can just see in the very bottom there where it says sync frequency. We've just turned on the frequency pulsing. So the sensor has a BNC cable with a TTL to the TTL port. So we're picking up that it's a 1 kilohertz signal from our signal generator. That signal generator is going to an amplifier. So we're pulsing 13.56 megahertz at 1 kilohertz, on off, through a matchbox to the chamber. And this is saying that doing the full 30 microsecond time resolution is actually only going to take just one second, because you have that 80 megahertz sampling rate. So even with all our averaging and everything going on, we can take measurements in a pulse really, really quickly. So if you think the chamber is ready, can you click on View Scan, and then we have to wait for the clean to happen. I think the relaxation time for the clean is like 20 seconds, so we have to wait a bit longer. It is always good practice to clean the probe before your experiment. And yeah, please run a scan. So there's still 10 seconds left on the relaxation time. So when you clean the tip, it's very hot, and you have to let it cool down, because when it's hot, you get more secondary electron emission. So to get better measurements, we want to, cool down again. Cool. So now this scroll bar is on a 30 microsecond time scale. And again, we can scroll through and see what this the IV curve looks like as a function of time. So you can actually see the plasma was up and then it collapsed, right? So this is the collapsing region, and this is when the plasma is there. So you get this ideal Langmuir curve when the plasma is there, less than ideal when the plasma is collapsing. Can you click on View Trends? And let's have a look at, say, the plasma potential. If you click on VP, we'll do that one first. So you can see there, plasma potential was about 30 EV, and then you can see that the plasma collapsed and then settled near 0. And then we probably picked something weird up near the end. Will we try electron temperature? So electron temperature is, again, very steady during the process. It spikes a little bit, so I'll explain that. It spikes a little bit when the plasma is off, and then it ramps down. And then the temperature. So the reason why it doesn't go completely to 0, I think we still have the other RF on, because we're powering both, because we can't get very much power out of our pulse signal generator, so we do still have the plasma on. But in any case, when the plasma is collapsing, your electron distribution function shifts down. You no longer have such high energy electrodes; they actually all shift down, and that's actually a really important stage in the plasma formation. What I mean by that is, if you have an electronegative gas, because the number of electrons at low temperature massively increases, you actually get this brief spike in creation of negative ion particles. So if you monitor, say, chlorine versus time, you'll actually, and during pulsing, during the on-off transition, you will always see a peak in like Cl minus or F minus or whatever else is there. Also, you can get more radical creation in that period. So that on-off section is creating more radicals, and radicals are an important part of your process. You have to understand that they are there too. They are reactive. They're not reactive ions, but they're reactive neutrals, and there's a lot of them. As a rule of thumb, if 1% of your plasma is ionized, probably 10% is radicals, something like that. Very plasma dependent, but roughly. So never forget that they're there. Can we have a look at maybe electron density? There we go. So we see the plasma takes a little while to strike. So it comes up, strikes, plateaus for a bit. So you can actually see the plasma is taking maybe a little over 100 microseconds, maybe 150 microseconds to strike. So plasma strike's not instant. It does take time. And actually, we're using an argon. If you're using like a nitrogen plasma or something, the strike time is much, much longer because, it starts absorbing rotational and vibrational energy before it becomes ionized. So striking takes longer, and you get a more complicated shape on the way up as different energy absorption modes take over and are saturated and so on. So molecular gases is much more complex. But you see, anyway, for the electron density, rising up, staying steady, and then you see it collapsing down, and then it's a little bit noisy at the end because our data is, there's barely a plasma there. Maybe ion density as well, Sarah, if you want to take a look at that one. Should be pretty much the same plot. Yeah, this is a bit smoother. So you have, again, the increase and a very steady decline and then settling. So this is really nice. And yeah, how are we doing for time? We actually only have about 10 minutes left. So maybe, what do you think, Jordan? Will we show a clean happening in the chamber just to see it in situ?
Yeah, no about it.
Sarah, can you make Jordan the host maybe? Or so there it is in our chamber live, and we'll run a clean process. So the plasma is still on, and there you go. So we draw in a lot of electrons and we glow red hot and white hot, and that's sputtering off all the materials there. And yeah, so that's what we were just measuring. Thanks, Jordan. Can you put me back as host, and I'll go back to the slides and the Q&A. Let me see if I can share a screen. And share. And full screen. Can you let me know if you can see the screen again, Nadia?
Yeah, we can see it.
Very good. So we're pretty much at the end. There's a lot more slides that we can go through. Like we're at slide 23 out of 43. So just very briefly to introduce you, like this is the probe that we had inside. So we have the feed through here where you can apply air cooling, collecting electronics, vacuum interface, and then the probe shaft, and then the tips are at the end. And we were using a single probe with DC reference tip. And we have this electronics box sitting to the side, and that was attached to the computer, which Sarah was sharing, and we're getting these nice IV curves. And that's not the only probe we have. We do have lots of different shapes and sizes of the probes. We customize them a lot. This is nowhere near comprehensive. Like we have these flexible ones for like big coating chambers or tools where you don't have a direct line of sight to the plasma. We actually have ones where it's planar on the bottom, so it's like a circular kind of puck shape instead of a shaft at the end. So that's really useful if you want to put it on a mounting arm and bring it around, like saying thrusters or whatever. We have linear drives. We didn't have one available today, but the linear drive interface with the software and does those scans spatially. So earlier on where we had we're viewing the trends versus time, with this you can view it versus space. We have a version available that goes up to 900 Celsius, but the default goes to about 220 Celsius with air cooling and about 120 Celsius or so with no air cooling. And we have other accessories like we can apply like these right angle kits. So that means you can probe up and down from the probe, left and right, do a rotation. Different probe heads. So we mentioned single probe, double probe. We didn't show any double probe data today, but they're useful for really high pressures or where you have no grounding in the chamber. We have spherical heads for low density plasmas. We have MAC probes, which can also measure plasma flow, and planar probes, of course, as well. All the specs are available on our website. And I'll just flick through these really quick. So like there's an example of people, like this is from Cyrem in France. They're a microwave source manufacturer, and they characterize their sources using our Langmuir probe. And they publish some nice data where they optimize the uniformity with our Langmuir probe. So they work well in microwave plasmas. People have mapped out what's their thruster plume profiles versus position. So you can see these really nice graphs where they're looking at, like this is even looking at the EDF at different points. and electron density, electron temperature, plasma potential over a plume. You can see this graph here where they swing the probe around the thruster plume. People looking at especially the decay period. I mentioned that's really important for radical formation and negative ion formation, which are, you need to know about those for etching. So people have studied those resolutions, showing the same data we did in our demo today. Like, it's easy to get this data. This is other examples of looking at the plasma strike time, the plasma decay time, and changing the pulse frequency and duty cycle. Like we produce these documents which have loads of reference papers. Reach out to us or go to our website, and you can get like all this really nice reading material. It's kind of like a cheat sheet for doing plasma measurements. And yeah, here's like a pulsed ICP, which is kind of important. How evolution happens when you're pulsing an ICP and you have an electrode down below. And then people are using it to optimize things like sterilization by changing the plasma parameters to maybe maximize the electron temperature, so you get the most production of OH radicals, so that does all the sterilization or whatever. Okay. And also people have been using Langmuir probes in high pressure plasmas, even all the way up to atmospheric, to get plasma density and electron temperature measurements for all this modeling. So I think because we're out of time, I will stop the presentation there, but we have a few minutes left for Q&A. So I will look at the questions. Carol, how's it going? Can you say a I can't pronounce that word, function as well as Maxwellian function to start off with the electron density? So as I mentioned, then there's two ways that the electron density the electron density is measured in two ways in the software. So it does have assuming Maxwellian, and then it has it taken directly from the EEPF, and you can even look at the EEPF. So, and I think this is done in the software. I'll have to actually reread the user manual, but I think this sort of thing is done. Rajesh asked, when you clean the probe, don't you expect the material to be etched off with long-term use? Does the user expect tungsten wire probes need replacement after n times of usage? Yes. So usually when you buy one of these probes, we send you a packet of like spare tips. I don't know how many's in the packet. It's like 10 or something. So over time, you do have to replace them. If you're using tungsten and argon, they last a long, long time. Like, we have our quality tips downstairs, and we probably had them for years. Don't use tungsten in oxygen plasmas. It will last 10 minutes. Use tantalum or something. But yeah, eventually you do have to swap out the tips, and not just when they're worn away. Like, do check it out. Like, if it looks like it's getting sharp, like we need to accurately know the cylindrical geometry in order to do the plasma models. So do make sure that those are correct. Samir asking, is electron temperature goes down as high temperature electrons are lost much faster to the wall? So maybe number of electron at lower temperature is the same or less. Yeah, so actually we probably should have spent more time on the EEPF. So it is a log scale plot, and the vast majority of electrons are low temperature ones, and you have orders of magnitude down to your high temperature ones. But those order of magnitude down is what's actually doing all the chemistry. It's those little, small percentage of the electrons are actually doing all the work, and most of the electrons are not doing very much. There's no video of the plasma. It may have taken did it not show on the screen? I could see it. I could see it on my screen. At the level of your intraslide and aura compensation, can you discuss two frequency compensation, or what happens when you're approached by two frequencies? Yeah. So basically, you have to put a number of inductors in line. And you probably, let me think about this. I might have to do the maths, but I think you want to have the low frequencies inductors first and the high frequencies inductors second. So the thing is, the more inductors you add, like, because the distance from the probe tip is getting further away, they become less effective. So as a rule of thumb here, we only do maximum 5 inductors in line, because to be honest, after that, they're just not effective. Because after that, you're already like 15 centimeters away, or 20, I don't know, like some long distance away, basically. So they become less effective. So yeah, if you have dual frequency, you can put multiple inductors in line, but I would put like maybe 2 and then the 13, and then maybe 4 and 27, like in that order or something like that. Sohail says slide 21 question. So I'll leave this open if you want to ask the question. Can you comment on present or future use of your systems to directly measure negative ion components in plasma? This is a good question, very interesting question. So how can we use Langmuir probes to measure negative ions? Because it measures electrons and it measures ions. What about negative ions? I've had some thoughts on that, but I haven't been able to get a negative ion plasma to check them out. But negative ions, they form at very specific energies. These I did my PhD in this, so I'm not going to remember the names of them. But there's the Feshbach resonances, and there's other electron attachment resonances, and there are very specific energies for specific molecules. And what I suspect is in the EEPF, if you have enough resolution on that, you should actually see dips in it because you have this resonance absorption at very specific energies. So if you really up the resolution in the measurement in that region, maybe we'd be able to say, right, you have this many negative ions or this electron loss absorption at least at these for these particular things. And by looking at where the energy dip is, because the energy dip should be unique for every single particle, like that's the beauty of it, it's actually unique for every atom and molecule, we might be able to judge what's there. So, but I don't know about this. Maybe there's something in the literature, but that's how I'd approach it. Can Langmuir probes be used to measure plasma nitriding? The chamber is normally a nitrogen-hydrogen mixture, 500 C bias volts minus 5 volt. Yeah, that's fine. We can do that. Maybe we can email these people, email yourself afterwards. We collect every single publication that uses our sensors. And I think we're well over 500 publications now. I think we have about 200 for the Semion, over 200 for the Langmuir or thereabouts. And the reason why we collect those publications is we pull out information from the paper. So we list what chamber type they're in, what kind of densities they're at, what pressures and gases they're at. So we actually have a list of papers with gases. So you could flick through them, see where people have used nitrogen and hydrogen, and pull out that paper and see what they did. But at 500C, yes, we can measure that. We have a 900C probe available. And yeah, we've measured in these type of chambers before. Software for DBD jet in the current software. Okay. Dielectric barrier discharges are very difficult to measure in. Very difficult because you have those really high voltages nearby the probe. We've tried a few times and haven't been successful yet. We have some ideas, but I'm going to say for now, dielectric battery, DBDs, measuring the source is difficult. Now, if you have a DBD generating a jet and you're measuring out in the jet, that's fine. As a rule of thumb, if you can stick for multimeters, you can get these thermistors that attach to a multimeter. If you can stick one of those in the jet and it doesn't collapse and doesn't arc, you can stick a Langmuir probe in. So that, as a rule of thumb, seems to be working. So yeah, and you have to use our Langmuir double probe. So that's in the software. When you start it up, you get the option of choosing double probe, and you can type in the one atmospheric pressure in the settings list, and then you can start doing atmospheric pressure measurements. But speak to us about it. We actually have user guides for how to do atmospheric pressure measurements. And the ion settings, ion mass, gas feed value, or plasma metal ion, which one? Okay, good question. So what if you use a mixed gas plasma, what ion mass do you put in? The answer is you put in whatever the dominant ion is, or a weighted average of the dominant ions. So that's the best practice. Are there any effects of magnetrons during plasma measurement? We've done lots of measurements of magnetron plasmas, not a problem. We have a lot of papers actually on magnetron sputtering, high PIMs, pulse DC, magnetrons driven by different powers. It's actually relatively easy. Don't see any problems. Could we place these probes close to the substrate surface? Yes, you can. Now, I'd recommend go for a Semion product, which you can place directly on the substrate and measure the ion neutral, like the ion and electron flux to the surface and the distribution of energies. That's way more useful for plasma surface interactions. But you can place it close to the substrate, but you must be aware that at different plasma densities, you have different sheet thicknesses. So if you have a low density, the sheet thickness could be so wide that when you get close to the electrode, you're no longer in the plasma, you're in the sheet, and you measure nothing. So it is plasma dependent. So what I'm saying is there's a minimum distance at which you can measure, and below that you'll get nothing. So you need to measure a plasma density up above, go down, 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 and then get as close as you can. But you can't get super close because of that sheath. High pressure plasma diagnostic is possible, but it also says DBD cannot be used on slides anymore. That is true. So what I'm saying is measuring at the DBD source, like measuring beside, like say you have the DBD wall, measuring beside that wall is a problem. But if that wall is enclosed in a capsule and then downstream from that, you have a plasma jet, you can measure in the plasma jet safely because you're away from the high voltages. Yeah, that's why. So that's where the confusion is. So it depends on the source and the jet. Source can be very difficult, but the jet can be easy if it's far enough away. David Boris asks, follow-up question on negative ions. Do the sheet model for ion collection change in electronegative plasma? I need to think about that. I need to check the maths. I'm not sure. I know what you're saying. Because usually the plasma potential is positive and it's negative. I have to think about that. I'll come back to you. Because yeah, the negative ions could easily be trapped in the plasma. Like when you actually produce particles in the plasma, like if you sputter some aluminium off a surface or something, those nanoparticles build up a lot of negative charge, and so much negative charge that usually get trapped in the plasma. Gravity will bring them down to the sheath area, but they won't fall through the sheath because it's like maybe plus 30 volts to 0. So they all get trapped above the sheath, and then when you turn off the plasma, all the particles just fall onto your substrate, and your next layer is full of particles. So yeah, but I get what you mean. We may have to look at negative ions more so by the impact it had on the electrons as opposed to measuring the negative ions directly themselves. Apart from given input, what's the difference between DBD and CCP? Big difference. Big difference. It probably out of scope of this call. Maybe we should actually do a plasma tool call. But as a general rule, like DBD is usually has these really, really high voltages on the surface. A CCP, yeah, has high voltages, but they're far apart, and you're very safe in the middle of the plasma. Like even if they're, only 30 millimeters apart or 20 millimeters apart, you're okay. And usually CCPs are RF driven. DBDs can be RF driven, I guess, but they're normally like really high voltage pulse DC. How can these measurements help one to understand sustained plasma consistent long-term months behavior? So to be honest, that's tool dependent and basically and chemistry dependent, process dependent. So you could use these to measure like what's the difference in the plasma between conditioned and non-conditioned chamber, or what's the difference between pre-clean, during clean, after clean. You can maybe look at how all the plasma changes. To understand, like it may be able to help you understand like what's an effective clean, what's an effective conditioning, like what kind of plasma, like when everything's working perfectly, what kind of plasma you have, and then compare with that later. But to be honest, I would recommend using our inline VI probes or one of those other things to do the constant day-to-day monitoring of the chamber impedance, because that's an indirect measurement of those changes. Like ultimately, you do have to service the tool. You do have to, do conditioning and cleaning. Like that's just unfortunately, that's just the nature of things. Can the Langmuir probe be used in a surface guard plasma reactor? I'm afraid I don't know what that is. A surface guide plasma reactor? I need to think about that. Maybe send me an email and I'll see what we can do. And will the recording of the presentation be available after the seminar? Yes. Impedance.com/videos is where we place all the webinars afterwards. And on LinkedIn, we post snippets from the videos. And Rob is saying, do this once every month. We do these regularly. So once every 6 weeks, we do a topic. Maybe actually, if you have a suggested topic, let us know. The next one of these talks will probably be in about 5 to 6 weeks. And also, I tend to travel around, so we can. I'm always happy to visit another a university or institute or whatever plasma company and meet people in person and do these things. So that's all the questions, and we've run over a little bit. So thanks very much, everybody, for attending. If anyone wants a copy of the slides, send us an email, and we'll put these up on our website in the near future. So, yep. Thanks very much, everybody, and until next time.